As you know, we have been arranging such programs ever since last October, almost every Sunday, uh, covering a wide range of topics, all the way from microphysics to macrophysics, from quark models to cosmology, with a view to educate our teachers and students about developments in variety of fields, so that they become a little more broad-based instead of just being confined to their own specialization. That is our objective. So we have been helped by various speakers from institutes, colleges, universities in our endeavor. And we have also arranged talks in Kannada, because we feel, at least at KPA, that ultimately even higher education has to be delivered in the local language. And NEP also says that in the interest of students, not because of any pride or prejudice or whatever, in the interest of effective communication, I think it is high time we bring in our regional languages uh, in the domain into higher education. This is happening worldwide. Even if you take a very small country in Europe, they arrange their lecture education in their own language, not English or German or French like that. Anyway, this is a problem we have to solve. There are so many issues we have to face and tackle, and that is a long time effort one has to put in. So today we are very glad that a specialist in atomic and molecular spectroscopy, Professor Jagadish from Karnatak University, Dharwad, has agreed to give a talk on Raman and his contributions and his life, and working as adjunct professor of physics in the Karnatak University, Dharwad. He joined the university in 1996 as a lecturer and continued there in various capacities as leader and professor, and retired in 2022. He also served as the chairperson of the Department of Physics and Electronics for 2 years, 2016 to 18. He was a member of the Academic Council of Karnataka University, and he has recently been elected a fellow of the Karnataka Science and Technology Academy, Government of Karnataka. He has been a visiting professor at BLDA University, Vijaypura, and group leader. He served as a group leader in the vibrational spectroscopy group of Department of Physics, Karnataka University. His major research interests are in the field of density functional theory and molecular dynamics modeling. He has also served as director of USIC from 2009 to 2015. And he has executed several projects, research projects, UGC projects, and DST funded FIRST project per program with a purse of 5 crores and so on. So he has guided 3 MPhil students and 11 PhD students to their degrees, and he has over 72 publications in refereed journals. He is a very popular speaker at colleges, universities, and he has also delivered several radio talks and published popular articles in papers and journals and so on. So a very active member in popularizing physics at various levels. So now I request Professor Jagadish Tonannavar to talk about Raman, the incredible Raman. Over to you, Jagadish.
Professor Kagli, thank you very much for giving this opportunity. How much time I have?
15 minutes you can take, 50, 50.
50, okay, thank you. Thank you. This talk is titled The Incredible Raman, for the simple reason that the Raman spectroscopy, that we shall see later, has had a tremendous impact on different subjects, disciplines, and the contribution that it has made in terms of not only theoretical framework but also wide number of applications as far as even art and archaeology. So this talk will demonstrate that how incredible Raman spectroscopy is. Today, Raman spectroscopy is a very mature science, gigantic science. It has grown enormously. As I said, now if you look at the journal of Raman spectroscopy, because journals are the barometers of contemporary work, how much is happening and then what are the wide applications and so on. The Raman spectroscopy is broadly that field which includes increasing number of rapidly developing techniques and an ever widening array of interdisciplinary applications. Namely, time-resolved, coherent and non-linear Raman spectroscopies, nanostructure-based surface-enhanced and tip-enhanced Raman spectroscopies of molecules, resonance Raman to investigate the structure, function relationships and dynamics of biological molecules, linear and then non-linear Raman imaging and then microscopy, biomedical applications of Raman spectroscopy, theoretical formalism and advances in quantum computational methodology of all forms of Raman scattering, Raman spectroscopy in archaeology and art, advances in remote Raman sensing and industrial applications, Raman optical activity of all classes of chiral molecules. Now, in the recent class of applications, even this art and archaeology have been included, apart from cancer research, where Raman is playing a very important role, and I think sooner than later, Raman technique would be available in hospitals also in diagnosing the disease. So this is the scope of Raman applications. So it speaks of the growth and development of Raman spectroscopy both as a principles and also application area in the last 90 years. Usually I try to cover, because this is my interest also, that how this scientific activity started in India. I'm not going too much into the past. Just if we throw a look at the Indian subcontinent, namely 18th century and then 19th century, there was nothing like any modern scientific research. So the British people had taken over India, they had subjugated the continent, but at the same time, they started doing something else also. Now this is the Calcutta in the year 1786, the artist's sketch here, and then came what is known as the Bengal Renaissance, where reformers like Raja Ram Mohan Rai began to see that the India must change in tune with what is happening in the West, and therefore he brought a lot of reforms. He worked with the British people and tried to bring changes, and therefore this is known as the Bengal Renaissance. But what came as a decisive period is the year 1857. We all know that. Sipai Dange, Kannadadalli ಹೇಳಬೇಕು, Sipai Mutiny. This was a very decisive period, because after this mutiny, the British Crown in England realized that the East India Company had mishandled the whole thing, and therefore it had to step in and then took major decisions. One of them is direct control by the Queen was imposed, and then uniform civil administration throughout Indian subcontinent was brought, and then of course introduction of British education system, and the East India Company was dissolved. And then how did it go about? First of all, you have to teach European literature, teach philosophy, culture, and also science, technological progress with Western Europe, effectively replace the native systems of education, and train people for administrative purposes. And then came the galaxy of people here, starting from Rabindranath Tagore up to Sharda Devi here. So all these people involved in what is known as socio-political awakening, including religion and then spiritualism also. It was at this time we had heard, we all know, Sir Jagadish Chandra Bose, and then Professor Satyendranath Bose, and then Professor Meghna Saha, and then Sir Prafulla Chandra Ray. Ray was in chemistry, and then others of course are in physics. They all rose to fame because of their fundamental work in physics, and of course Jagadish Chandra Bose also did work in botany and also wireless telegraphy, for which is well known. What about Raman? Raman comes later. But during this period, there was scientific activity during the 19th century. what British people did, many people came to India and they started doing a lot of surveys, not only civil survey but also mineral surveys and then topological surveys and then so on. They published many monographs, journals. They also established scientific societies like this, Asiatic Society and then so on. And then people began to attend universities and colleges. These three universities were established around that 1857 after the Sipahi Mutiny. And then of course one solar observatory was also established in Kodaikanal. It was at this time one practicing physician in Calcutta, Dr. Mahendralal Sarkar. He was not a celebrity nor he was a scientist himself, but he was trying to toy with the idea of creating something what he had heard, that is the Royal Institution of Great Britain. This was established in the year 1799 by an Act of Parliament, and then we all know that Michael Faraday was there. In fact, he conducted all his experiments and made discoveries, and he also became the director of research at the Royal Institute. And then of course stalwarts like Lord Rayleigh and J.J. Thomson, and then subsequently many people were associated with this institute. So Dr. Mahendralal Sarkar was toying whether I can create a similar institute in India, that is in Calcutta, for the benefit of young people to do research, because people otherwise had to go to England at that time. So with great difficulty he raised money and finally he was able to build this. This is known as the Indian Association for the Cultivation of Science, where Raman discovered the Raman effect. So this was founded on 29 July 1876, and then it began to function. Initially, Dr. Sarkar invited people, as shown here, to give public lectures, because he used to collect money from the public and then use it for building the center. But nobody came there to do research. That was his ultimate plan, because all these people, especially Dr. Bose and Ashutosh Mukherjee, of course, was a legal luminary. He went on to become Vice Chancellor of Calcutta University later, and then P.C. Ray. They were all attached to Presidency College, so they were well established scientists there. So they had no mind to come here and then do research, and therefore the center remained like that without much of any activity. It was at this time Raman entered. This was a great moment, because Raman came there as an Assistant Accountant General in the Finance Department, Government of India. Now before that, let us throw a brief bird's eye view of his early life. He was a very brilliant student, did his BA at Presidency College, Madras, winning gold medal in English as well as in physics. Then he was unable to go to England for higher studies because of his unphysical fitness there. He was disqualified, and therefore he had to do MA there only. That he completed in the year 1907 at just 18 years. And this is the photograph with his friends, and then this is a group photograph of his friends and then teachers at the Presidency College. Raman was a very diminutive figure at that time. And then this is the college where he studied, and this is the lab on the right hand side where he did his experiments. Raman was so good, he was far ahead of his teachers, and therefore he was given exemption from attending classes. And therefore he spent all his time in the laboratory trying to do something on his own. Whatever interested him, he did that. But he didn't idle away time. Instead, he selected a problem and then worked on them. For example, here, the unsymmetrical diffraction bands due to a rectangular aperture. We all know that we consider normal incidence of the light ray on the diffraction aperture, and then we study the diffraction pattern. But instead, he said, what happens if the rays are at oblique incidence? That he did, and then he wrote up a paper, and that is also an interesting story. Let me not go into that. And then he submitted this to Philosophical Magazine there. And he had written it so well, and the experiment that he had done it, very interesting science that he had produced, it was published here. And this is the reference of that paper. Then he went on to do one more experiment. That is, how does one measure the surface tension of liquids using an optical method. Because Raman, throughout his life, he was always comfortable and then he had a forte in two areas, that is optics and sound. So the curvature method of determining the surface tension of liquids that he did, and it was a novel experiment. He used optical technique and then he published another paper in the same journal, Philosophical Magazine, 1907. So with this background, he went to Calcutta as an assistant accountant general. And of course, let me be very brief. There he started his work. Then on his way back home, he used to see Calcutta, very interesting Calcutta at that time. And one day, it caught the attention of his tram there, the Indian Association for the Cultivation of Science. He wondered, what is this building for? So he went in, and then he inquired. Then he was told the story of Mahendralal Sarkar, what he had done and so on. Because Mahendralal Sarkar by 1904 had died. In fact, he had died very unhappy because his vision was not fulfilled. This is the Lord Rayleigh to whom Raman had submitted his papers. This is the correspondence that he had with Lord Rayleigh. And Rayleigh thought that Raman must be a faculty member at the Presidency College. Only later he realized that it was a student there. So Raman married and then settled in Calcutta. So he took permission to work here before and then after office hours, and then began his scientific work. Without any assistance, without any mentorship whatsoever, Raman on his own began the work. So whatever interested him, he went on doing that. You may not believe the rate at which he published papers, doing whatever it interested him in sound and in optics and magnetism, took him to the Western world. He made in 10 years, he made a great name there. He was not doing any modern physics experiments at that time, because we all know that the period 1900 to 1925 was a period in which quantum mechanics took its birth, theory of relativity, lot of exciting things were happening in Europe. But Raman was not doing any of these things because he was so much handicapped by the circumstances. But nevertheless, whatever he did was publishable, and then he went on publishing the papers one after another. In other words, he produced good science from whatever was available with him. That was how Raman worked. In fact, there is a lesson here also that even in adverse circumstances, one can still produce a good science. Now, these are the broad areas in which Raman worked: optics, sound, magnetism, and then fluorescence study, 1921. How did he get to this fluorescence study? He was traveling to England by ship because there were no aeroplanes at that time. So he had to spend roughly 2 weeks on board. And then, of course, he was an avid watcher of nature. He always carried two things in his coat pocket. In one pocket, spectroscope, small spectroscope, and then in another pocket, nickel prism. And he used to wonder the blue color of the sea waters. That's how it started. And then when he came back home, he began to study the molecular diffraction of light by liquids. That's how his motivation was underlined there. Then he began the study. He started various options in the study, trying to change different gases and then liquids. Interestingly, the Raman effect had been actually seen before 1928, but it was just brushed off as some kind of a weak fluorescence until the moment came. We all know that the Rayleigh scattering, the blue color of the sky, is due to Rayleigh scattering. We all know that. And then this Rayleigh scattering was also seen in the laboratory. While doing so, Raman observed a very weak fluorescence. Fluorescence, as we all know, that when a material absorbs radiation of some wavelength, then it emits radiation of longer wavelength. So initially, whatever new thing he had seen or his students had seen, it was mistaken for some kind of a residual fluorescence. But subsequently, when the same thing repeated, then he began to doubt that there must be something new here, some new effect. In fact, one of his students, very brilliant student, was K.S. Krishnan. And K.S. Krishnan noted in his diary, especially the events leading up to the discovery, that was in the year 1927 and 1928, that how by repeated experiments the whole thing was confirmed. So they were studying fluorescence, but they were led to a new effect. This is the equipment that Raman used at that time. In fact, he struggled a lot to set up this experiment because at that time, as I said, he had no money to buy equipment, no grant whatsoever. But by people's donations, he used to raise money also, and then he used to contact rich people in Calcutta and then buy whatever he wanted. And then by 1921, he was professor at Calcutta University because he had made a name, and then he was invited, and then he resigned his government job and then joined the University of Calcutta as a professor. Now, this is the experiment that Raman did. This is a typical, the old type experiment. He used the sunlight because even he had no mercury source. This Raman scattering is a very weak scattering. One can say almost 1,000 times weaker than the Rayleigh scattering. And therefore, it was a very difficult experiment to do. And he had to rely on sunlight. And sunlight that was collected through an optical telescope. And the telescope became the source. And then the scattering was observed. And we all know that sun doesn't remain stationary. And therefore, telescope had to be moved so as to provide the beam exactly on the opening slit of the spectrograph so that the experiment was not disturbed. So it was a very tough experiment indeed, but nevertheless, it was done very meticulously. Now in this diagram, we can see here, monochromatic radiation was produced here using a violet filter from the sunlight, and then this violet radiation falls on the sample. It may be, let us say, acetonitrile or even toluene or even benzene or whatever, any organic solvent. And then what you see here at right angles to the incident radiation is two radiation. One is the scattered light, that is same thing as the original one. It is called Rayleigh scattered light. And then in addition, there is a green light came there. By using the filters, Raman confirmed that the moment you block this violet radiation, this green immediately, instantly disappears. And the moment you block this green, violet is not there, right? So by this complementary technique, this is a very simple thing. He was able to confirm that he had indeed seen some new effect. And of course, measurements were done later. But before that, he was very quick to recognize the significance of the new event. And then these things were also measured. For example, Rayleigh scattering. In the case of Rayleigh scattering, the scattered radiation wavelength doesn't change or frequency, but it is polarized. In the case of fluorescence here, the wavelength changes, but the light is not polarized. But in the case of Raman scattering, radiation is polarized as well as wavelength also changed. So this is a fundamental difference among the three. So this was confirmed. Now this table gives us the distinctions among the three phenomena. And this is again a typical Raman experiment that was done much later. After it was announced, the people began to repeat the experiment. Now here is a mercury source, the old-fashioned mercury lamp, which used a lot of strong ultraviolet lines, of which this 2536.5 angstrom line was isolated, and then hydrogen chloride gas was excited. This upper part is the mercury spectrum, and the lower one is the mercury plus the Raman spectrum here. This is a photographic reproduction, and therefore you will see many things there. But let us look at what we want. Now this Raman spectrum has very interesting thing. Now this is a line with which the HCl gas was excited. And then you will see here 2752.8, 2752.8 line which is much longer wavelength than this excitation line, and then this is a new line that is seen there. Now what does it actually tell us? This is called a Stokes line because the second term comes from the fluorescence, where the shifted wavelength with respect to the original wavelength is called a Stokes shift. So the same terminology is applied here. We'll come back to this little later. So once everything was over, Raman did not lose time. He immediately announced the discovery in the form of a small note that is submitted to Nature. Initially it was rejected, but Raman convinced the editor that indeed it is something new worthy of publication. Then finally it was published here. And then subsequently, of course, the detailed note was submitted, and then paper by Raman, and then so on. At the same time, more or less after 2 months, 2 Russian scientists did the same thing. They had seen the same effect, but of course in quartz crystals. But having published it for the first time here, Raman had the first claim, and therefore it went to him, the credit went to him. Now this is the lab where Raman did his experiment, and these are the spectra of various liquids that he had taken. In fact, we don't know what these spectra stand for. Maybe he must have taken this Raman spectra of some organic solvents. Now this is the paper, the first paper that he communicated to Nature. It is called a new radiation. Now this is the same spectrum that I had shown earlier. What is the importance of the Raman spectrum? Because there is a new Raman line appearing there with a wavelength different from the initial wavelength, and if you take the wave number difference of the two and subtract them, this is what we get, 2080-81 centimeter inverse. Now if you measure the IR spectrum of the same compound, it will also give the same value. And there we attribute that to vibrational frequency of the molecule. That means from the Raman spectrum, you get the same thing. So the Raman shifts essentially correspond to the vibration frequency of the molecule. So this is the first thing that was realized. And then this is the typical Raman spectrum here, where Stokes line and the so-called anti-Stokes line both are shown. In the previous spectrum, of course, you don't see anti-Stokes line because it is too weak to be seen there. But it is expected. If you use laser line, then definitely you will see the anti-Stokes line as well. So this is the empirical explanation of the Raman scattering. Now the vibrations frequency, which corresponds to this Raman shift here, is given by this, we all know this basic formula, in which there is a force constant here, and this is the reduced mass of the molecule. That means the vibration frequency depends very much on the force constant, which is the measure of the stiffness of the bond, chemical bond. Which means that if you can measure the Raman frequency, then you can also deduce the force constant of the given molecule. Now this is the table where we can see diatomic molecules I have taken for simplicity, the various diatomic molecules with the corresponding Raman frequencies here, vibration frequencies. And then you can see here homonuclear diatomic molecules, that is molecules having atoms of the same kind, H2, N2, O2 and F2. Because of their symmetry, they don't produce any IR absorption, in which case Raman is the only thing on which you rely. So similarly here N2, O2 and then F2. You can see the Raman frequencies are measured here. Similarly, the other diatomic molecules whose Raman frequencies are measured here, and also force constants. Force constant can be determined from this. Of course, we don't determine the bond lengths because that comes from another Raman spectrum that is known as rotational Raman spectrum, of which I will talk about it later when we discuss the model. So it was in the year 1930 that the discovery was hailed as a new discovery, and then many people confirmed that in their respective laboratories, including very well-known spectroscopist R.W. Wood at the Johns Hopkins University, and he called it as the Raman effect. And since it has been called the Raman effect, and this is the Nobel Prize that was given to Raman. Now let us look at what is the theoretical basis of this Raman scattering, both classical and then quantum. I do not wish to go into the technicalities here, just to outline what it is. Before I proceed, let me tell you something about this. When we talk about Raman spectrum, Raman spectroscopy, it is invariably understood that it is a vibration Raman spectroscopy. That means Raman scattering associated with the vibrational motions of molecules. In addition, molecules also rotate, and molecules also have electronic motions, and hence there are rotational Raman scattering and also electronic Raman scattering. But rotational Raman scattering is a very special thing, and it is not as widely usable as the vibrational Raman scattering. And therefore, when we say Raman spectroscopy, we always mean it is vibrational Raman spectrum or vibrational Raman scattering. Electronic Raman is still more difficult, and it is very, very remote. But it is there. So in principle, all these motions are associated with the Raman scattering here. So I am showing here the vibrational motions of molecules here, with which the Raman effect is associated. We all know that the harmonic oscillator model, that means you have to assume the molecule to be harmonic oscillator and then do all the calculations, and that gives us the vibrational energy of the molecule. And from this it follows that you have a series of vibrational levels which are equally spaced. And that means a diatomic molecule, for example, vibrates with a single frequency. Now if you take a triatomic molecule, then of course you can calculate it has got 3 frequencies because of vibrational degrees of freedom. So the basic mechanism here is, when radiation is incident on a molecule, we all know that the incident electromagnetic radiation is a sinusoidal wave consisting of electric and then magnetic fields. Let us consider only the electric field because it doesn't interact with the electrical property of the molecule, the magnetic field. Therefore, only the electric field is considered here. So this electric field, when it comes in contact with the molecule here, it induces electric dipole moment in the molecule. So this induced electric dipole moment is coupled with this electric field. So that is the basic mechanism. Now we assume that this induced electric dipole moment is proportional to the electric field. And this proportionality is the measure of the polarizability of the molecule. In other words, how much of Raman scattering takes place, the intensity of the band, and then so on, is all determined by this polarizability of the molecule. The simple picture of the classical model is that if you consider molecule with this induced electric dipole moment and then do this simple calculation, it leads us to this expression. So there are 3 terms. The first term corresponds to Rayleigh line because it says that this term has the same frequency as the incident radiation. Now the second term says that this has a lesser frequency than the exciting line. So it's called Stokes line. Now the third one is, this term shows that there is a more frequency coming than the incident frequency, and therefore it is called anti-Stokes line because it's not expected in the fluorescence, and therefore the term anti-Stokes line is coined here. So you have a Rayleigh line and then symmetrically situated Stokes line and then anti-Stokes line. Now from this expression it is clear that both are displaced symmetrically about the Rayleigh line. That means if you calculate the wave number difference, the magnitude is the same, whether the difference between the Rayleigh line and the Stokes line or anti-Stokes line and the Rayleigh line, the vibration frequency is the same. However, the difference is that the Stokes line are much stronger compared to anti-Stokes line. We shall see this why. There is also a quantum mechanical basis for this, that is the Kramers-Heisenberg dispersion theory of radiation. So I am not going into the details of this because this is too technical here. All that I can say is when radiation interacts with molecule, and we all know that the molecules are excited here, so there is absorption, they go to higher states and then they return. Now this Heisenberg dispersion theory says the process of absorption and then emission of light radiation by molecules are one photon processes, because in every transition the radiation field either loses or gains a photon, while the molecules undergo a corresponding change of either electronic, vibrational or rotational states. In general, scattering event, that is the field loses an incident photon characterized by this energy and then another photon characterized by this energy. Now what happens? The scattering process is regarded as a two-photon process. This is with regard to Raman scattering because the incident photon of specified energy, polarization and propagation direction is scattered so that the emerging photon may have a different energy, polarization and propagation direction. This is the fundamental difference between Raman scattering, Rayleigh scattering and then fluorescence phenomena. So the transition probability, if one calculates per unit time that an incident photon is scattered into a solid angle as a photon, scattered photon, that leads us to what is known as the Kramers-Heisenberg dispersion formula. That means from these considerations, the Raman scattering, or it's also called the incoherent scattering of light radiation, follows. If you read Raman's paper, in fact he had come to know that whatever effect that he had seen in the lab could be explained on the basis of Kramers-Heisenberg dispersion theory. So he made a reference to that. He also said that it looks very similar to Compton scattering, and therefore he called it as the optical analog of Compton scattering. There is one more scientist here, that is Arnold Smeckel, who had explained again the same phenomena before this Kramer-Heisenberg had given their dispersion theory. Though we don't talk about it, but it was there in 1923 itself. And then the remaining things follow. Now George Plazak is the one who actually gave a systematic theoretical approach to Raman scattering. What we know today, classical and then quantum mechanical approach, is due to George Plazak. There is also one more book, D.A. Long, Raman spectroscopy, in which he has given the Plazak approach to Raman theory of Raman scattering. Now this is the schematic diagram of the Raman scattering when you use the quantum picture. In the case of IR absorption, the incident radiation is absorbed, and therefore there is a transition here, and then we see an infrared absorption band. But in the case of Raman scattering, you can see here the molecule returns without changing its wavelength, or as shown here, it comes to the upper vibrational energy level here, and therefore there is a loss of photon. This leads to Stokes-Raman scattering. In the third instance, if, let us say, there happens to be a molecule in the excited state and which is scattered here, that means it takes energy from the incident photon and goes up here and then returns to the lower state. Here the photon is being added, and therefore this gives us anti-Stokes-Raman scattering. That means you have a line of higher frequency or shorter wavelength. Now I made a statement earlier that the Stokes lines are intense, more intense than the anti-Stokes line. That is because of this Boltzmann distribution. We all know that when at a given thermodynamic equilibrium, there are more number of molecules in the lower energy state than in the upper energy state. So from this it follows that the anti-Stokes-Raman scattering is less intense than the Raman scattering because you have less number of molecules available for that transition. The whole picture can change if you go for non-linear Raman effect, where you can create more molecules in upper state and then make anti-Stokes much stronger. So all these things possible in the case of non-linear Raman scattering. This is again the intensity, because intensity, as I said, is always an issue in the Raman experiment, and therefore one has to use a very bright or very intense light source. That's why when lasers were invented in 1960, in fact Raman got rejuvenated so much that it threw up a variety of topics and then branches, including nonlinear Raman spectroscopy. This is again the same vibrational spectrum, equally spaced levels, and then you have this vibrational selection rule. That means only those levels for which this vibrational quantum number changes by either +1 or -1. That means only adjacent vibrational levels are involved in the transition because they produce this vibration frequency. But if you go to polyatomic molecules, the number of vibration levels multiply. So it becomes more complex, but the basic thing remains the same. This is the typical Raman spectrum. It is a modern Raman spectrum of carbon tetrachloride using a laser. This 488 nanometer comes from argon ion laser, and when the carbon tetrachloride is excited, you will see this beautiful spectrum here. In fact, if you measure Raman spectrum on the Raman spectrometer, you don't see this kind of spectrum. This is only illustrated just in conformity with what you had seen earlier. That means on the shorter wavelength side, higher frequency side, you will see anti-Stokes Raman lines with lesser intensities, and on the longer wavelength side, you will see Stokes line with more intense lines here, or intensities. So in order to demonstrate that, this spectrum is shown here. Now this is the same carbon tetrachloride spectrum plotted like this. This is what we do in the routine Raman work. So all these Raman bands are shown here, and then this is the structure of carbon tetrachloride. If you know the spectroscopy, we say the symmetry of this carbon tetrachloride is TD bond group. So it's a high symmetry bond group. If you imagine a cube and place this carbon at the center of the cube, then at one end here you have two chlorine atoms sitting, and the opposite, diametrical opposite, you have one more pair of chlorine atoms sitting there. So it's called a tetrahedral structure. So this is a well-known spectrum because you get a very good Raman spectrum for this carbon tetrachloride. Now the same thing I have superimposed here on the photographic spectrum, and then this modern Raman spectrum here. So this is a Rayleigh line, which is very intense. Then on both sides you will see here Stokes line, anti-Stokes line, and then Stokes lines here. So the intensity's contrast is very much apparent here from the spectrum. What is the importance of Raman spectrum here versus infrared spectrum? Now same carbon tetrachloride, when it is measured, you will see there are 1, 2, 3, 4, 5 bands here on this side. Raman gives 5 bands, whereas IR is giving only 3. So this is where Raman assumes its significance. That means where IR is not possible or fails, Raman works. And this picture shows what are the different ways in which carbon tetrachloride molecule can execute its modes. The first one refers to stretching. That means this 458.7 centimeter inverse is here, and this refers to the stretching mode of the carbon tetrachloride. And this is asymmetric stretching here, which is 768 there. And then the remaining modes follow, like scissoring and then wagging. So all these modes are grouped into, depending upon the type of their vibrations, into stretching, antisymmetric stretching, rocking, wagging, and then torsional, and then so on. So this is how a spectroscopist normally classifies the normal modes. Benzene, we all know, is a very important molecule, and its structure is of course known to us. You can also establish the structure of benzene from the spectrum, both IR and Raman spectrum. Now here comes an important thing. Benzene, as we all know, highly symmetrical molecule. In terms of group theory, we say it has got D6H symmetry here. It has got a center of symmetry. That means there comes a rule, what is known as a rule of mutual exclusion. That means the bands seen in the IR are not seen in the Raman, and then vice versa. And therefore, by combining both, you can deduce the structure of a given compound. In this case, you can say that it has got a center of inversion. Now look at this Raman spectrum. There is a very strong band here, 992 centimeter inverse. Suppose if you are measuring the Raman spectrum of a given organic compound, let's say aromatic compound, and if you see this band here, which is characteristic of the aromatic ring, that means if you have a strong Raman band like this, then you can say that the ring must be aromatic there. So this is how the spectrum is correlated to structure. We talk of spectra structure correlations. So from the knowledge of Raman spectrum, you can also deduce the structure of a given molecule. And of course you can do a lot of other things. I will list them later. Here I am showing you the animated vibration modes of benzene. So these are all the different modes of benzene. If we calculate the number of degrees of vibrational modes, it comes to 30. So benzene can vibrate in 30 different ways. However, there are only 11 frequencies. So 30 modes share these 11 frequencies. And then this is water. Water, as we all know, has 3 modes. And then the first one is the antisymmetrical. You can look at the way it is vibrating. The second one is very evidently symmetrical, and the third one is bending. The 2 bonds bend about this oxygen atom. And then you can have a Raman spectrum and also IR spectrum here. So for this water molecule, all the 3 modes are Raman active, and also all the 3 modes are IR active. That means you will see them in both the spectra, unlike what we discussed in the benzene. Now the interesting thing comes when you have another molecule, a very well-known molecule, carbon dioxide. Carbon dioxide, CO2, you can deduce the structure of CO2 in the sense that the carbon is in the middle and the 2 oxygens are on at the periphery of the carbon. That means the 2 are situated about the carbon atom. How does one draw this conclusion? Same thing. If you record the Raman spectrum again, we see that this 2349 band is not seen in the Raman, it is seen in the IR. Whereas this 1388 is not seen in the IR but seen in the Raman. And again one more in the IR but not in the Raman, like this. So this mutually exclusive appearance of the bands tells us that the molecule is symmetrical. So this is how one can deduce the structure of a given molecule. So these are all simple examples. When it comes to complex systems, things become more complex because the number of bands in this spectrum multiply, because they are also very much dependent on the number of atoms and bonds. Whatever it is, let us summarize. Raman is strongly complementary to IR. IR is sensitive to functional groups present in the molecule and polar bonds. That means the bond is slightly polar. Raman is sensitive to backbone structure and is very much dependent on the covalent bonds. If the covalent bonds are distorted, then Raman is very sensitive to that. That's why Raman is very popular, because it gives direct evidence of the structural changes. It can also be used to study aqueous solutions, because where there is water, it's a nuisance to IR, because you get hydrogen bonded large, very broad band which masks. It becomes, let's say, some kind of, it eclipses many details in the spectrum. But Raman is not sensitive to water, and therefore you will see very clear bands in the spectrum. The intensity of spectral features in solution is directly proportional to the concentration of particular species, and therefore Raman is very, very specific to that. Specificity is very much or high in the case of Raman compared to IR. And Raman spectra are generally very robust to temperature changes as well. And then of course sample preparation is also very simple now. These days new Raman techniques are facilitating the preparation of sample much easier than it used to be in my days also. So you can just take the sample, directly place it on the sample chamber and then record the Raman. You will get excellent Raman spectrum. Now let me skip some of these things. Raman instrumentation. Discussion on Raman spectroscope is not complete without this component, because ultimately we have to measure Raman. Traditionally we have a dispersive Raman spectrometry where the Raman spectrometers or monochromators depend very much on the monochromators. Either it is prism based or grating based. Of course prisms are almost out of use, we have only grating based. Now we also have Fourier transform based Raman spectrometry, which is much faster than the conventional dispersive Raman. Though dispersive Raman has its own advantages, still it is used as a dispersive Raman for some applications. Then we have microscopy combined with Raman. Therefore, we have a confocal Raman microscope where you not only image your sample but also record the spectrum. We talk of what is known as the chemical spectral images. Then of course you have a time-dependent study, time-resolved laser Raman spectrometry as well. That is much more complex thing because it involves so many other details. Now the principal components include light sources. Now these days we use only lasers. Then monochromator systems. You need a very sensitive detection systems because Raman, as I said, is a very weak. So signals are very weak, and therefore you have to have very sensitive detector systems. Then sample illumination is very critical to Raman scattering. If the sample is not aligned properly, then you get nothing. So that is another important thing. In the case of IR, there is no issue there. You can simply pass the radiation through the sample and then you get the spectrum. But Raman is not like that. So you have to illuminate the sample using what is known as appropriate geometry. Then sample handling, as I said, one can do these days very easily. Then data signal processing techniques and then interpretation. Now these are all now facilitated very much by very powerful software. Now these are the typical laser sources for Raman work. Now increasingly Nd:YAG lasers are used. These modern Raman spectrometers. It gives 1064 nanometer, the corresponding wave number is 9395, because 1064 nanometer means you are away from the visible spectrum. Therefore any colored compound which otherwise fluoresces, gives fluorescence, you can avoid that, because fluorescence is a nuisance to Raman. And therefore to avoid all that, 1064 nanometer is recommended, and invariably most of the Raman spectrometers come with this Nd:YAG laser and different versions of this Nd:YAG laser. And then of course diode lasers are also becoming popular because they provide these wavelengths 980 and then 1480 as well. This is a typical Raman monochromator system. This is a dispersive Raman. So this is incident laser beam scattered by the sample, enters the chamber here. This is the first grating. Radiation is dispersed, then it goes multiple reflections, then one more grating here. This is mainly to increase the signal to noise ratio. Therefore you get high quality Raman spectrum. Then you have a photomultiplier tube here where the Raman signal is detected. This is a kind of spectrometer that I had used. This is the monochromator, very popular, Zerny-Turner type. You can also have one more grating here, single grating, double grating, and then triple grating. So they are accordingly called single, double, and then triple monochromators. But these are all very expensive. The Raman is very expensive equipment compared to IR. In fact, it is 5 to 6 times costlier than normal IR spectrometer. This is the Fourier transform based Raman spectrometer system, where you have Michelson interferometry incorporated into the system, and therefore you do away with conventional optical system like grating and so on. So essentially it produces an interference pattern, and that interference pattern is, by applying the Fourier transform, you can extract the spectrum. So from amplitude domain to frequency domain. So that gives you excellent Raman spectrum. So this is much faster than the conventional dispersive scanning type Raman spectrometer system. I said in the beginning also that intensity is an issue here. So intensity depends directly on the fourth power of the frequency of the radiation, or inversely fourth power of the wavelength of the radiation. And therefore, you have to have a proper selection of the radiation source, and then there are other things like spectrometer parameters and then so on. So the intensity of the incident radiation matters here. That's what I said. We use very powerful radiation sources for the Raman work. Sample handling is, of course, is done by various techniques. Let me not go into the details. We have many detector systems, including high gain photomultiplied tube. Photodiode arrays are now common. Charge coupled devices is also common but expensive. Now indium gallium arsenide is a semiconductor diode, is also used for routine Raman. Then you have lead sulfide. Suppose if you are measuring, let's say, very large Raman shifts, high frequencies, then this gives us the wave number region towards the high, lower wavelength and then higher frequency there. Then this is germanium detector. This is a very powerful. This can be cooled, and therefore it gives Raman spectrum down to 50 wave number. So that is its advantage. This is the Raman spectrometer system we have. We procured this at Karnatak University by paying rupees 54 lakhs there at that time. This is a combined. On the left hand side you have IR, and then the right you have this Raman. Raman microscope. As I said, microscope is combined with Raman spectrometry. This is another Raman microscope, very expensive, more than 1 crore. But it does a lot of good work. You can image a sample and then record spectra of very, very different kinds of samples. I'm going to show you a couple of samples applications here. So these are the broad applications in molecular spectroscopy, mainly to identify functional groups, which is a very routine thing now. Then of course by that you identify the compounds, unknown compounds. Low frequency modes in solids. For example, if you are measuring frequency, wave numbers below 200 centimeter inverse, then IR is not going to work there. So Raman works. So you can correlate low frequency Raman modes to structural aspects of solids. In fact, we have done in our research work the analysis of low frequency Raman modes as well. Symmetry and structure determination. I took the example of benzene and then carbon dioxide. Thermodynamic properties can also be deduced, and then the polarization states of the Raman bands. In the beginning we saw that the Raman lines are also polarized, and therefore you can use that property to also determine the symmetry of the given modes. This is Raman versus IR. Two typical spectra are shown here, and this is the range, normal range, from 4000 to 200 centimeter inverse spectral range. Similarly, this is the Indian here. What is to be noted here is, you can see very strong Raman band here. So there is hardly any IR here. Similarly, IR is very broad here, but Raman is very sharp. So where there is a lot of problem here, because IR is very, very sensitive to moisture, but Raman is not. That is its strength. And therefore you get very sharp Raman bands. Similarly here, I pointed out that if there is a band here around 992, then definitely there is aromatic ring here. So that band you can see here. So such spectra structure correlations are applied routinely to do the study of structural and then other studies as well. Now here comes the Raman imaging technique. Detection of low concentration of binder. This is the Raman map of an anode superimposed on an optical microscope image. Now the colors here represent various chemicals. Styrene, butadiene, rubber binder, that is red here. Graphite, green. Then acetyl black, shown in blue here. And the relative concentrations are determined by the map, namely 1%, 97% and then 2% respectively. These are the materials used in the battery technology. So Raman image gives us this spectral image, chemical image of the materials here. So this is how Raman technique is used in battery technology research also. The same thing is shown here. This is the image. Here is the Raman spectra. The same colors are shown here and the different Raman spectra. So you can see the changes in the Raman spectrum from one material to another material. Because Raman spectrum is characteristic and therefore you can identify what are the functional groups in each of the materials here. This is the Raman spectra of the key components in a tablet. High quality images of their distribution. Suppose if you take a tablet from any pharmaceutical shop, you can take a Raman spectrum readily and then you can see how the chemicals are dispersed in the tablet. Here I have not identified, I am just showing you an example. This is another Raman image of human esophagus where red shows the tissues, dark blue here. There is epithelial cells here. Yellow here you can see they are the lamina propria, and magenta lipid here, the cyan color here, they are the mucin part of the esophagus. That means the different components in the material, human esophagus, can be imaged and then you can do the spectral study. So the same things are shown here. This is the tissue. One section is shown here, lipid, and then mucin, epithelial, and then lamina propria. This is the geological sample, earth science. So Raman can also be applied there. Quartz, this is called the tiger's eye. So when this is examined using 532 excitation line, the Raman image shows the quartz, SiO2 here. So you can see this cyan color. Much of it is all quartz here. Then there is also inorganic carbonates, yellow, H2CO3. Here you can see. So it shows the chemical distribution in the rock sample. And then this image is 47 mm wide, 26 mm deep, and then 3 mm high. So this is the advantage of studying the geological samples using the Raman imaging technique. Here I am showing you some video. Hope it will play. Takes time.
Open the file. You say you want to open. Open.
Yeah, I open, yeah. Is it visible?
No, nothing. Not visible.
Okay. I think
Not playing. Video is not playing.
it will play now. It is taking a little bit longer time. It will play.
Okay. Yes, sir.
Has started?
He has to close this, is it? Okay. I will tell. I will tell him. Yeah. Okay. I'll tell him. Okay. Okay. I'll tell him. So it is suggested you stop sharing the screen and then open the MP3 MP4
Yeah, yeah.
file. Then it will work. Stop sharing the screen. Play only the MP4.
Yes.
Try that, please. Stop sharing. Go to the video file and play.
Actually, it played, but I think you didn't see that.
Oh, is it? Okay. Doesn't matter.
Because once I come out, I think sharing stops.
Yeah. Hello.
Hello? Okay, I think let me skip that. Video always has a problem.
So one suggestion is you go out of the PowerPoint mode and go to the MP4 screen sharing only the particular video file. I don't know if that is possible. I don't understand. Anyway, if that is a problem, then leave it.
Yeah. I think I will skip and.
Okay.
Longer the PPT, the delay.
So you have to stop sharing the screen and only the MP4 file then can be played. You please try that if possible.
Yeah.
Stop sharing the screen. You are then use only that particular. That is for share only the video file. I don't know if that is possible. That's a problem, I think.
Yeah.
Yeah, I think we can move on to the next.
I will move on.
Yeah, next topic or whatever. Anyway.
It's hanging.
So you have to stop sharing, otherwise it will then again share again. Stop sharing and then try sharing again. If that works. Try again, or anyway we are coming to the end of the time also.
Yes.
Not in time. So you can try to summarize in maybe 5 minutes or so.
Yes.
Last slide. Last slide. We are not hearing you. Are you trying to do something?
Yeah, I think there's some connection problem here.
Right. Then
I think.
you just summarize, please.
Yeah. Okay, I wanted to show a couple of slides about how kidney stones compositions can be done using Raman. We have done that ourselves.
Oh, very good.
So that I wanted to show.
Unfortunately, it's not working.
It's working, yeah. One thing is I can come out and then start again.
Yeah, that is what is suggested. Stop sharing and then try resharing. So that can be done quickly. Yeah. You open it, trying to open. Yeah. Double click to enter the full screen. Yeah. Double click.
Yeah, I've done that.
Not seeing yet. Yeah, now we can see. Yes. Yeah, go ahead, please.
Yes, you can see. Yeah, similar example.